Assalamualaikum dan datang. Saya Muhammad Taufik bin Buang, BI 24110291. For question 1, we are given an 8-bit message with having error. Correction. The store check bit is 0101, 4-bit, and the retrieve word is 01001101 at bits. So in total there are 12 bits, including the check bit. So we put it in a table. So we classify it as check bit 1, check bit 2, that data bit 1, check bit 4, and so on and so forth. So we see that there are 8 data bit and then 4 check bit. So we will check each check bit one by one. So first check bit, we see check bit 1. So check bit 1, we see here the least significant. The first position is the least significant 1. So we get the data 1. We look for data 1, data 2, data 4, data 5, and data 7, which have 1. It is mostly significant bit. So D1 XOR D2, D2 XOR D4, D4 XOR D5, and D5 XOR D7 or. And when we see that 1 XOR 0 XOR 1 XOR 0 XOR 1 equal to 1, and we do the same for check bit 2. Check for the bit in the position 2 that have 1 in it, so that will be data bit 1 here, F1, data bit 3, data bit 7, data bit 4, data bit 7, data bit 6. So we XOR data bit 1, data bit 3, data bit 4, data bit 6, data bit 7, 1 XOR 1, XOR 1, XOR 0, XOR 1 equal to 0. The same for check bit 4. We look for the third bit in the third position. The third position. Look for the third position, which is data bit 2, one in the third position, data bit 3, data bit 4, and data bit 8. This one. So we make it 0 XOR 1 XOR 1 XOR 0 equal to 0. Same for check bit 8, data bit we see data bit 5, so we look for the fourth position, which has 1. We see data bit 5, data bit 6, data bit 1, and data bit 8. So we XOR them, 0 XOR 0, XOR 1 XOR 0 equal to 1. So equal to 1001. So then we use this bit to find the syndrome word by using XOR. XOR it with XOR the fetch check bit with the origin, the store check bit, which is 0101. So we XOR it. We get 110 or equal to, we can see here, bit position 12. So there is an error in bit position 12 or at data bit 8. So we see data bit 8 is equal to 0, so we flip it from 0 to 1 and correct the data. Okay? So the original data is 11001101. Okay, for the question 2, we are given x equal to -14 and y equal to -6. We should answer the following using the 5-bit value of the multiplicand m, the multiplier q. So first we convert 14 into decimal into the decimal, and 14 is in decimal, and convert it to binary. So we convert it to binary and then we negate to get the positive of that number in binary. So, or in other words, here m is equal 100 We negate by this, by flipping the number and then adding 1 to it. The same for -6. We first convert it to binary, then flip the number 1 0 to 1 1 to 0, and then add 1 negate, so we get the q is 110110. Right, then we will compute the product using this table, the product of x times y, using a 5-bit word and both algorithm. So the initial value of a is 0, and the q, as we have calculated, is 11010, and the q -1 is 0, and the m is 100100. So first we see that here and here is 0 0 0. So using the both algorithm, we shift the number, to the right. So that's for the first cycle, right? And then for the second cycle, you see that it is the value of q and q -1 is q -1 is 10. So we subtract m from a, and get 0110 and then this stay the same, and then we shift to the right. So this here become shift to the right, 00111, this becomes 00110, then this become 1 because we shift to the right. And for the third cycle, we see here that the value of q and q -1 is 01. So we add m to a. So we add m to a. So we add 00111 add 100 so it becomes 11001, and this stay the same, after we add a plus m, we again shift to the right for the third. So become 10010. This stay the same because it's the sign bit. The one here stay the same because it's a sign bit. And then we see that the value of q and q -1 is 10. So we subtract it we subtract m from a, so subtract 1 1 1 1 1 0 0, subtract 0 0 1 0, we get 0 1 0 1 0. This is the same, and then this is the same. So then we shift again to the right, so this become 0 0 1 0 1, this become 1 0 0 1 1, right? And then we see for that's the fourth cycle, and then here's see the value of q, and q minus 1 is 1 1, so we only shift to the right, so it become the value becomes 0 1 0 1 0 1 1 0 0 1. So the product is 0 0 0 1 0 1 0 1 0 0. For the third question, we are given a equal to 10 and b equal to negative 5. So we are told to compute the product of p divided by b using a 4-bit word and restoring division algorithm. So first we convert q. We convert q, or in other words a, into binary. 10, which is 10, become 10 10. Then m, which is b, negative 5, we modulus because we treat in the restoring division algorithm, we treat every negative number as a positive. So we just convert the 5 into binary, so it becomes 0 1 0 1. Then we put it in the table in the initial value. A is 0 0 0, and q is, as we can see here, 0 1, as we can see here, 0 1 0 1 0. So first we shift to the left, so it become 0 0 1 0 1 0, and then this is we unknown. After that we subtract a minus m, so 0 0 1 minus 0 1 0 0 become 1 1 0 0. So because the most significant bit is 1, so we restore a back with previous one to the previous set, which is 0 0 1, and then q0 this place become 0. So the value of a is now 0 0 1, and the q is now 0 1 0 0. So that's the first cycle. Then the start of the second cycle, we first shift to the left, so it becomes 0 0, the value of a becomes 0 0 1 0, then here become 1 0 0, and we don't here. So we subtract a again, which is 0 0 1 0, subtract m, which is here 0 1 0 1, so we get 1 1 0 1, then 100 100 1 0 0 1 0 0, and we don't know, a blank place. So because here is still 1, so we will restore back the value of a with the value of a, which is 0 0 1 0, and add 0 to the place. Okay, that's the second cycle. For the third cycle, again we shift to the left, so the value of a becomes 0 1 0 1, then here becomes 0 0, blank place, and then we subtract the value of a, which is 0 1 0 1, subtract m 0 1 0 1, so we get 0 0 0 0. Here we don't know, we look here and then we see that the value is 0, so we didn't restore the stat of A. The value of A is not restored, and here become 1. Q0 become 1. Okay, for the last cycle, the fourth cycle, we first shift to the left. So it's still A is still 0, 0, 0, and then Q is 0, 0, 1, blank space. Then we negative, we minus A minus 0, 1, 0, 1, M, A minus M, 0, 1, 0, 1. So we get 1, 0, 1, 1, 1, 0, 1, 1, and Q is still the same. So we see here that the most significant bit of A is 1. So we restore it, and Q0 become A. So this is the last one. A is the remainder, and Q is the quotient. So there is 0, 0 remainder, and the quotient is 0, 0, 1, 0. Alright, for the fourth question, we are given a processor that uses 16-bit instruction format with the layout shown here in figure 2. The content of memory entry register R2, R4, R5 are given in the figure, and the opcode is 0xD2. The register field specifies R2, and the address field is 0x4D. So the first question is immediate addressing. What would be the operand value for the if the immediate addressing is applied? So we see here that they said that the opcode is 0xD2. So in immediate addressing, the processor will extract the operand directly from the instruction. So the instruction is the operand. So as the opcode is 0xD2, the operand value inside the 0x4D is also 0x4D. So B, what if direct addressing is applied? So indirect addressing, so we see here that the opcode is 0xD2 and 0x4D, sorry. So the processor would first look for the memory 0x4D, which and then the operand value is it will look first it would look at the memory address, the memory with the address of 0x4D, and the operand value is the value that the memory address is pointing at. So we can say from the figure 0x4D is pointing at 0x1. So the operand value is 0x1 if direct addressing is applied. Alright, for C, if register indirect addressing is applied, we can see here that the specified field is R2. So first, the processor will first look for the content inside of R2. So we can see here R2. In R2 there is 0x2b. Right? 0x2b. From 0x2b, the processor would then refer to the memory with that have an address of 0x2b. So we can see here 0x2b, and the operand value will be the data that is pointed by the address 0x2b, which is 0x5c. So the operand value is 0x5c if the register indirect addressing is applied. That's all for me. Thank you.